already said all of that, except for the last bit, which in deeper water we do lay the pipelines on the seabed. And if you remember last time when we talked about pipelines or seabed geology, in deeper water you tend to have very soft clays. And then you get a phenomenon called axial walking, lateral buckling, which I won't describe the process of axial walking. Basically the pipeline heats up, and if you can imagine, heats up, cools down, heats up, cools down a bit, so it starts to walk along the seabed. And in some cases it actually generates a buckle. And there's been a lot of work done on that in the last few years. So that's really a deep water soft clays problem. And as I said, shallower water pipelines tend to be trenched for insulation and protection. So starting with surface laid pipelines, we need to consider the lay process and how that might affect the embedment which occurs during the actual pipe lay. Axial and lateral friction, which again, particularly in soft clays, is heavily dependent on the depth of embedment which is experienced. And those are some references. That one is quite good for surface laid pipelines, but easily accessible. It's on Google Books if you go onto there and go to those pages. I've certainly always managed to find it on Google Books when I go in, but you maybe don't want to do it too many times because it does lock you out. And that's a paper probably best for trenched pipelines if you want to look at that. I've also got some references at the end which I'll mention, but there's a DNV document which is pretty good as well. So, lay considerations. What do we have to consider when we actually lay the pipeline on the seabed? The pipe's laid from a moving vessel, so they're moving as they touch down on the seabed. You're familiar with J-lay and S-lay, are you? Yeah. Uh-huh. The weight of pipeline is a function of a number of factors. The seabed properties, strength of the seabed soils, the submerged weight of the pipeline, also things like the vessel motion and the lay catenary profile, and actually the stiffness of the pipeline. If we just as you're, oops, sorry, I've gone too there. Yeah, so you're aware of J-lay and S-lay, so I won't dwell on that, but very different angles of lay, and often used in different water depths as well. But the important thing here is that the pipelines, as they're laid, if there's a vessel motion, they're moving up and down as they touch the seabed. If there's any horizontal motion, which could be currents, that could move the pipeline side to side. So you end up with this, that's your pipeline, but it can't be going anything within that, moving around anywhere within that sort of envelope. And just to illustrate how much they do embed into the seabed, that's a 24-inch pipeline offshore India on soft clay. And you can see how it's gone into basically half its diameter just by weight and lay process. You will often, or nearly always, get a slight berm there if it embeds as well. It's basically displacing the soil and pushing it out over. If you've got harder seabeds, you get very little penetration generally. So the embedment is really a thing for soft clays, and it's something we need to understand to determine the actual axial resistance and the lateral resistance as well, because obviously if you've got it embedded, it's got a greater contact length, so that gives it more cohesion of the clay soils, if you remember. and the partial embedment also sort of stops it moving sideways so easily. And there is a little equation to help us calculate the touchdown weight of the pipeline, which is the first stage in sort of calculating the embedment process. It's not too difficult. That's actually in the Governeck and Randolph book, that equation. But most of the stuff we know, V max touchdown weight and W dash submerged weight of the pipeline, we know. What we want to get out of the equation is basically that value. We know the E for the pipeline in the second moment of area. Hopefully we know the lay tension, or have an idea of the lay tension as well. And that's a variable, I think typically around 200. But there's more stuff in the book. However, the point I want to make is this is not a precise science as such. It would be nice if it was, but in reality the pipeline is the depth of embedment is quite variable, and that's the sort of depth of embedment which has been experienced in this particular pipeline's case. We've got, and that's, you know, the sort of bounds of what we expect, or the bounds that was actually recorded. So what we're really trying to do is get a sort of sensible average value and working it out along the pipeline length. It does make it very difficult to predict exactly when a pipeline is going to walk and when it isn't going to walk. But we can at least have a first stab at it. So the notation that we use, and I've tried to be fairly consistent with this notation throughout these notes. D is the external diameter of the pipeline, including coatings, and D is the width, D dash rather, is the width of the contact length, if you like, at the base of the pipeline. And small w is the depth of embedment. It's one of those things that use W rather than Z, which is often the common one as well. So how we actually might calculate the embedment is using these equations here for sands and clays, based on V-ult, which is the touchdown load of the pipeline. So it's not the weight per unit length. V-ult will probably be about twice the weight per unit length. And there's some constants in the equations, a bit of a fudge. SU is the undrained shear strength at the base of the pipeline, the depth we expect it to go to, and that will be increasing with depth, so again it becomes a bit of an iterative thing to actually calculate it. Now we've calculated the depth of embedment. What we're actually going to use in design is probably the pipe soil friction. And that's required for, you know, calculating hydrodynamic load and the stability of the pipeline actually on the seabed, and then it will go into any walking or buckling analyses that we might do. In clay soils, I don't know if Mo did much on this. We usually consider sands to be an undrained material and to have a cohesive strength, an undrained shear strength we call it. And the notation for that can be SU or CU. We tend to use it pretty indiscriminately. I think SU is probably what you'll most commonly see. But if you go to America, you're more likely to see CU. However, over time, the clay does actually act as a drained material, so you do have to consider both scenarios when you're designing your pipeline. The undrained behaviour will be the immediate behaviour, but over time it might migrate towards a drained behaviour. In sands are a granular material that work purely on friction, so we only consider the drained case, the actual friction between the sand particles or the friction between the sand and the coating of the pipeline. Now, in harder soils, the pipeline penetration is very low. So that makes life easier because we can consider the contact length here as a simple strip footing. Now, and then from that we can calculate W dash. Now I'll talk a little bit about foundation design tomorrow. Might even start that lecture today if I get a chance. But basically, as the width increases, your bearing capacity per linear metre of pipeline is increasing. So in a crude sort of way, on a hard seabed, it's a reasonable estimation to take that width as being the applicable contact width. The other point I would make on a hard seabed, particularly sands, we're considering the pipeline's soil friction as a frictional material, so it's really just the weight of the pipeline that's driving the resistance to both axial and lateral movement. And that probably goes for a lot of most hard, stiff clay sites. You will tend to have a sand veneer, so it does not that often that you've got to consider embedment of the pipeline in soft clay or a cohesive type resistance in soft clay. Because the seabed's fairly hard relative to the weight of the pipeline, W becomes small, and it doesn't really make a big impact on the lateral stability calculations, that depth of embedment. You don't get a lot of added resistance from the embedment depth, so it often a safe view is to ignore depth of embedment. And here is some guidance on the sort of friction values that you might use. So you weight your pipeline, say 5 kilonewtons per metre or something, so you can calculate the axial and lateral friction with these type of values. The D50, has Mo done anything on grading curves with you? I know I put some up in the last lecture. Anybody?
It's just what we went through with you.
Yeah, right, okay, yeah. So we do a grading curve, run the sand through a series of sieves, and the median grain size is D50. So that's, if you like, the size of sand where half the sample is passing through a sieve of that size. If the D50 is less than the pipeline roughness, the coating of the pipeline, so you've got a concrete coating which is fairly rough, then the sand particles will interlock with that coating, and we can use the full friction value of the sand. However, if you have a smoothly coated pipe, PPE type coating, it's smooth, and the sand particles are more like that. They're not interlocking with the coating of the pipeline. So you have to reduce the friction value to allow for that, the absence of the interlock. Okay. Clay soils, most of the time it's going to be a smooth coating because clay is very fine, and therefore you're not getting the same level of interlock, so you'll be tending to use these sort of numbers here as a range. In soft clays, it's most critical on soft clays, we want to calculate the axial resistance. And undrained shear, if you remember, is more about area of a sample than the actual contact pressure. You need a certain contact pressure, but in soft clays, it's more about the area. So if sorry. That's our pipeline and it's embedded to there, see. Then that our contact length is that. And we'd use an average undrained shear strength. So the resistance would be SU, the undrained shear strength, times an alpha value, an adhesion factor, which typically 0.5 to 1 for very soft clays. It's how much you get some remolding on strength. So when you initially lay the pipeline, you might reduce the strength by then apply an adhesion factor of 0.5. Over time, that largely excess pore pressure from the lay process disturbing the soil, that will dissipate and the strength will recover. So you might increase it to say 1. And then, so your resistance would be R equals SU times your adhesion factor times the area, which is that length times 1 metre effectively. It's the contact area per unit length. And it may increase. You remember I showed berms around the pipeline, so if you have that sort of effect, then your contact length may increase like that. So you may get a higher axial resistance than you expect. Yeah. Now, with that, or putting all that together, if you have a drained, an undrained response, when it first tries to move, it's probably been laid on the seabed a few months, maybe a month or two before it actually carries oil. So that the initial disturbance from the lay process will have reduced, some of the strength in the clay will have recovered. So it's actually reasonably resistant to movement, so you get quite a high load to actually mobilise that first movement as the pipeline heats up. Then, because that movement has the effect of softening the clay, remoulding it again, it can drop down again to this value, which, as it says, is dependent on how fast the pipeline is trying to move. Then you switch the pipeline off, it cools down and contracts, so it tries and pulls itself back, and then it will go back along that line. But then when it tried to move again, it could go up like that and back, and that can happen several times. So it's really. I was having a discussion with somebody. We were doing a research project yesterday, and to predict when a pipeline will actually walk is, I wouldn't say it's completely impossible, but it's very difficult to be 100% sure, almost impossible to be 100% sure. If you have a drained response, if you have a sandy seabed, it's much, much easier because you tend to get that sort of response. It mobilises itself and then starts to slide, and the friction is fairly well defined. So it's a much easier type scenario to understand. Now, with the pipeline walking or moving axially, that axial movement at some point has to go somewhere. And what can happen is it actually buckles. That was laid straight and it's buckled out over. And the only thing that's really stopping it is the soil. Usually introduced by thermal compressive stresses, but it can result from laying on a slope or laying round curves. One of the things that came up yesterday was the pipelines can actually walk uphill depending on the flow regime and the seabed soils. And that buckle ultimately, because you've got a weaker point there, it tends to feed into the buckle, so you can actually rupture the pipeline ultimately if you're not managing it properly. There are quite a number of models available for lateral resistance in soils. A safe book, it's probably just about finished now actually. The ongoing is probably a bit not really correct, but that was a project which ran for about 10 years. Has anybody heard of safe book? I saw you nodding your head. Anybody else? Oh, I think, sorry?
Yes, question.
Yeah, of course.
About these drained and undrained responses,
Yeah.
I couldn't understand this one. I mean, I didn't understand this.
Okay.
We are saying that clay, yeah, in offshore.
It ultimately will have a more of a drained response.
So it's drained. It has drained clay in offshore. It has drained response and undrained responses.
The initial response is undrained. Okay, if you apply a load when you share the pipeline moves initially,
Okay.
that will be an undrained response.
Okay.
Okay.
It's laid.
Yeah, when it's laid, and then when it moves again for the first time, it's usually, if it moves quickly, it's an undrained response. And what that does is generate, if you think of the clay as this soggy, wet collection, which water, a bit like a sponge, but water doesn't run through it very easily. You sort of squeeze it a little bit and some water slowly runs out, okay? As that water runs out, you get more to a drained response, and it becomes more of a, like the interface becomes more like a frictional type response.
So the formula that you showed before, it's like resistance to the.
It's, well, I expressed it as a phi dashed of an angle of friction. Do you mean in those ones?
Yeah, no, after that.
That,
Yeah, this one, yeah.
Yep. So SU is the undrained shear strength. Okay? And that would apply for most purposes. That's the right thing to do, particularly on soft clays. In stiff clays, you'd be much more likely to use a drained response, a friction angle, okay, which would be something in the range 20 to 30 degrees, say, whereas sands will tend to be sort of 27, 28 for a very loose sand, up to about 40 degrees for a dense sand, very dense sand. Okay?
Yeah,
So, okay, you happy?
Yeah.
It's. I don't want to get too bogged down in detailed, but it's important that you're aware that clays can behave in both a drained and undrained response. Drained being a longer term resistance to movement. So, lateral resistance in soft clay, there's several methods around. That's the one in Governeck and Randolph, which is the reference I gave you at the start. And it looks fairly complex, but in reality it boils down to these equations where W is the depth of embedment, D is the diameter, V is the current weight of the pipeline, and V max is the maximum weight it's experienced. Because if you think about it, the V max might be when it's been laid, where it's quite heavy. If you've hydro-tested the line, which is normal, it'll be heavier then. Then if it's a gas line, it'll be lighter when it's in service. Or it might be a multi-phase line which has slugs of oil and then slugs of gas, so it varies. And H is your, I can't remember, have a look at it. Horizontal resistance, and F is the force which is applied. I'll have to check that, but I'll do that tomorrow. It's in the book anyway. Now there are various ways to control buckling of pipelines. One of the ones that is used is to put a sleeper under the pipeline at intervals and effectively snake lay the pipeline. So if you snake lay it, you know, because you know the temperature that you expect in the pipeline. By snake laying like that and putting a sleeper at those 2 points, when the pipeline expands, it expands that way and that way and that way and that way. So it's expanding into the buckles so that it will try and adopt that shape. And by managing the spacing of those sleepers and lifting it out of the seabed, you're effectively releasing the lateral friction, so it'll try and slide there. And you can manage, by managing the spacing, you know how much the pipeline's going to expand, so you can then work out how far it'll deflect and whether that's acceptable or not. There are some issues to be aware of with that, and this happened to BP on one of their jobs. Because it's going up and then down, you're promoting slugging of the contents of the pipeline if it's multi-phase. So the oil tends to collect just before the sleeper, and then the pressure builds up, and then all of a sudden that slug of oil goes through and gas follows it, which is changing the weight of the pipeline, and that cyclic change of weight stresses the pipeline potentially, and it actually starts to trench itself into the seabed. And I've seen, I don't actually have a copy of the picture, but I have seen a copy of the picture where the pipeline's actually about that far down into the seabed because of this change in weight, and it's just gradually broken the, it started to fatigue the pipeline and had to take the sleepers out. So another way of doing that is actually just to put some buoyancy on the pipeline so that you lift it out of the seabed a little bit. Or if it's walking, you can anchor it at one end, or in some cases at intervals along its length, to try and stop it actually walking along the seabed. Right, sorry, I've moved a couple of slides around. You've got this in your presentation, but or in your notes, but further on. What are the reasons for trenching? Well, protection and flow assurance. Obviously, by putting the pipeline below the seabed, you're protecting it from certainly fishing gear. Fishing gear is very rarely designed to penetrate to any depth into the seabed, but also ship's anchors, that which is a much more aggressive form of thing. And if a ship's anchor hits a pipeline, it could well rupture the pipeline. So by doing that, you're protecting it. Thermal insulation, if the contents is hotter, it's usually easier to pump, so that makes life easier. It reduces the risk of hydrate formation by just simply reducing the pressure you've got to overcome. You can often get a lot more production out of a pipeline. Stabilization. Pipelines are subject to loads due to waves, particularly in shallow water. I mean, it's not really a significant thing in deep water environments, but in shallow water you can get quite significant loads on the pipeline which need to be resisted. And if as an example, the Nord Stream pipeline was designed as a surface laid pipeline. They did some more sums and decided they had to trench it, which cost the client quite a lot of money. And then again, by trenching, you can reduce the wall thickness and concrete weight coating requirements, which is another factor. As an example of just how much benefit you get from trenching a pipeline, then there's two ways you can do it. You can put a expanded polyethylene type coating, PPE coating on the pipeline, and if that's say 4 centimetres thick, it has a very low K value, a low thermal conductivity, which means that it transmits very little heat. So it does make a big difference in keeping the pipeline warm. It is expensive to apply, and because it's quite thick in reality, it's reducing your capacity or the length of pipe you can get on a real lay vessel, because you've got a drum size there, which if you may be okay, but if it goes over a certain value, then you've got another trip to port to pick up more pipe and pick up the end of the pipeline, connect it, lay away again. So you get a benefit from it. However, if you have, say, a metre of soil over the pipeline, and then the soil is much more conductive, I accept that. But actually, at the end of the day, that metre of soil is nearly twice as beneficial as a PPE foam type thermal insulation layer. So there is a clear advantage in just trenching a pipeline for thermal insulation. Sorry, I just want to jump around a little bit, maybe not in the best order. Now, as an illustration of just how significant that thermal insulation can be, this is a pipeline. It was actually a real case from the Gulf of Mexico, this. So it's 10 kilometres long, really. That's the temperature profile. If it was just laid on the seabed with no insulation. So with no insulation, temperature came in at, no insulation, that one, 65 degrees C the oil was coming in at, but it very quickly cooled to the ambient temperature of the seawater. If you left it on the seabed and had 25 millimetres of insulation, it did actually keep the oil much warmer, down to 30 degrees C. But simply trenching it without any insulation, it kept much warmer. It only dropped 15 degrees C over that 10 kilometre length. So that's, really quite a small drop over 10 kilometres. one of my clients actually trenched this pipeline. I haven't got the trencher profile, but I think it was pretty much as expected. Just by trenching the pipeline and backfilling it, as they were it was a live pipeline, the production went up 30%. You know, so it made a big difference to the client in terms of how much quickly he could produce from the reservoir. I'm not saying he got more oil out of the reservoir, he just got it quicker, which is overall the cost saving, because your overhead costs of actually running the field are quite significant. So as I said, you've got better flow characteristics, less waxing, and increased production.
Sorry, what's the KP?
KP is kilometre post. So it's 2 kilometres, 4 kilometres from the well.
Okay, so it's like say buried one. It has higher efficiency. With
the buried.
Oh,
Yes,
I
sorry,
mean
the buried one
yeah.
with no insulation is the most efficient one because it keeps the oil warmest.
But the insulation it's a bit lower. Why?
Because that insulation is on the seabed, but it's not buried.
But that one is buried and with insulation, or
But buried, no insulation is that one.
okay.
Just laid on the seabed, but with an insulation coat around it.
Yeah, I know,
Yeah.
but the thing is, in the previous slide, it was like insulation has less conductivity, so there was
If less conductivity, higher resistivity reduces the heat loss. Do you see?
yeah.
Okay. So it depends on how you express it. Lower, higher conductivity there, but lower actual heat loss. Okay. The conductivity and thermal resistivity are just the inverse of each other.
Excuse me.
Yeah.
You said your client had their production increased by 30%
Yeah.
by trenching the pipeline.
Yeah.
So was it, it was already existing,
Yep.
and then they undertook a project to trench it?
Yes.
Wasn't it a very expensive venture?
They obviously thought it was worthwhile. I think they probably got a deal. It was actually a shell job. It's not that to trench a line like that, 10 kilometres, say, is yeah, 7 to 10 days work. By the time you do a survey before you trench it. You've got, and then in that case you'd have to do a trench collapse pass, which I'll explain, to actually put backfill on the pipeline, and then you've got to do a survey to prove that the pipeline's at depth and how much backfill you've got. So there's 4 operations, if you like. So it does take a little bit of time, but the ship would be about $80,000 to $100,000 a day. So less than $1 million, and in the grand scheme of things, if they're producing quicker, that's probably well worthwhile for them. Okay. When we talk about protection, we're primarily talking about trenching or protection from fishing gear. Obviously extensively performed in the North Sea, but also other areas as well. Trawl gear is quite heavy. The trawl doors this is an otter board rig. The boat's up there pulling these 2 tow warps, and the doors are like that, so they're being pulled to sort of hold the net open, and they can be 4 tons. Now, the fisherman doesn't particularly want to them to be sinking into the seabed, because that costs them money, but they when they turn or stop or anything like that for any reason, then they can sink down, so they are a bit of a risk to pipelines. And they're pulled at fairly high speed, 4 knots. It's about, give or take, 8 miles an hour. So, you know, it's a run, if somebody running, if you like. And that would damage a pipeline, potentially, particularly a small diameter pipeline, because inherently a small diameter pipeline will have a thinner wall thickness and a lower I value, etc. So there is quite a risk of damage. Now, one of the issues that comes out of insulating the pipeline, we're keeping it hot, but by keeping it hot, we're increasing the axial compressive stress that is generated in the pipeline. When the pipeline's laid, it's going to be at the ambient water temperature. So when you put oil through it, particularly hot oil, you, just as with a surface laid pipeline, you're getting a compressive stress which is trying to push it together. And the upheaval buckling force, what you get is if you get a slight out of straightness, so the pipe profile may not be perfectly flat, that buckling force will concentrate there, just like a surface laid pipeline, just like there. If you've got that, is effectively acting as a buckle, so it's feeding into that point. Same with a buried pipeline. And what we're relying on is this soil up here to try and hold the pipeline down. Now, we can use the soil from the trench, or spoil if you like. The issues there are the properties aren't well defined. We might have done the best survey in the world before we've laid the pipeline, but that's measured the strength of the seabed soils before they've effectively been pulled out of the trench and then pushed back in. So there's understanding those properties is a bit of a challenge. There's also, the advantage is that they are relatively cheap. It's their material just to push back into the trench, and so in reality not that difficult to push that soil back into the trench. And they do provide thermal insulation, not those backfilled soils. They do. The exceptions might be if you've got a particularly coarse material or a very stiff clay which breaks out in big lumps. That might not give you quite the same level of insulation. The other way of preventing upheaval buckling is with rock dump, which is basically crushed rock. So it's rock of typically 1 inch or 25 millimeters to 150 millimeters size. Advantages are, you know what the properties are, but it's expensive. You've got to get a ship, particularly to come back from shore, from a quarry in usually Norway, to put it on the pipeline. And because it's quite a coarse material, water flows through it easily. So the water, you get a thermal convection current from the hot pipeline, which just basically cools the oil down very quickly. You can use sand, but it's not ideal using sand. It's much more expensive to actually purchase because they're not set up to load sand into a vessel in the same way that they are set up to load rock into a vessel. And also because you're putting it down at a fall pipe vessel, which I'll show later, you've more chance of sand being lost, so you've got a higher wastage. Upheaval buckling mechanisms are now fairly well understood. The real research probably started in the late 1980s, and they were published as a series of papers at OTC, which is Offshore Technology Conference. So you've come across OTC papers before?
Yeah.
Don't really know? Yes? No?
Yes.
Yeah. Right. Since then, that was based on some model tests really with samples, typical soils or representative soils. The idea of centrifuge testing caught on, where you get with a relatively small sample, you can model at smaller scale and a pipeline and the upheaval buckling resistance of the soils. I've mentioned Dave Cathy's paper before, but that's got some information in it. And then DNV RPF 110 provides some good guidance on upheaval buckling analysis and how you should approach it. The next few slides are based on that, and I do think it has some conservatism in it. It is currently being revised and updated, and for some reason they've stripped out a lot of stuff which should be in, and I don't really understand why. But what I'll show you now, we talk about now, is the current practice. So again, really, this is intended primarily for your notation. We always talk about the outside diameter of the pipe, including any coatings. So D or D tot is D total. They're both the same thing in effect. You have a trench and hugely idealized trench geometry there, usually filled with soil. The cover height is taken from the top of the pipeline to the top of the backfill. And you might get that from survey information, where you can see down and see the level of the pipe and then the level of the backfill. And in some cases, we might add, or usually it would be an engineering analysis if you've got to add additional backfill to resist upheaval buckling. So, if we look at the upheaval buckling resistance of a soil, we end up with an equation like that. And in a sandy material, it breaks down into three essential components. That's our top of our backfill, and our pipeline is there. And if you can imagine a plane of soil like that, the first section there, gamma dashed HD, so that's D. And that is H. The weight of that soil there is, can you see this okay?
Yeah.
Yes.
Okay, so that's gamma dashed HD, that's the weight of the soil. Height, diameter, or width, times the submerged unit weight. The next bit of the equation is this bit here. And what that represents is this little bit in the corners of the pipeline. It's actually pretty small in terms of the contribution it makes to the upheaval buckling resistance. So if you look at D squared, is that effectively that square there, times a half is that bit, pi upon 8 minus pi upon 8. If you take the area of that, that's pi d squared upon 4, isn't it? So you divide it by 2 pi d squared upon 8. So you end up with half, because you're taking that bit off, minus pi upon 8. And then you multiply by gamma dashed. I think it works out about 0.07 times gamma HD, or with something of that order. It's a small proportion of the total resistance, but it's in there.
So this gamma dash, second gamma dash, is the same as the first
Yeah.
one?
Yeah. Submerged unit weight of the soil. It'll usually be a little bit lower than the value you get from a site investigation, because by digging it out and pushing it back in, you've remolded the soil. Then what you have in this section is that. Now, we're talking about sand here, so we're talking about a frictional material. So if I plot out the in situ horizontal stress with the stress which is being applied to that shear plane, and that shear plane is effectively H plus D upon 2. Okay, so that's where that bit comes from. That horizontal stress is expressed as HD gamma dash. Oh, sorry. What is it? K naught gamma dashed times H is your horizontal stress at any point. Now the horizontal stress is defining the, it's a frictional material, so the horizontal stress is deriving the total friction that you have, which is a function of the there's a gamma. That's from. I changed these equations for this lecture, and there's a gamma dash missing from that equation, and that's straight from DNV. I'm sure that's what's thrown me. The frictional value is a function of the friction angle, tan phi dashed. So you multiply that by tan phi dashed times K naught, and that section there is actually your F value. Okay, so that's just a function of those two components. And then 3. So can I just check something? Sorry, I just want. No, I've got it. I'll check this for tomorrow, because I'm sure that equation's wrong. It should be gamma dashed in there. So that equation then becomes gamma dashed F H plus D upon 2 squared, because you're multiplying that area, okay, by you're squaring it, and then dividing it by 2, because you're taking the full width, and that's the pressure there. That's K naught H D upon 2 squared. And you divide by 2 because it's a triangular shape, but you multiply it again by 2 because you've also got the same on the other side. So you end up with that equation with the gamma dashed in there. I'm really quite annoyed about that. There is, in DNV, there is this little table which gives you F lower bound based on a range there, and phi, that phi is the range of friction angle for the backfill. I think particularly because most backfills will tend to be fairly loose, 0.1 is very conservative for the backfill.
There is a gamma dash.
Sorry? Sorry?
On the last one, there is a gamma dash, if I'm not.
Yeah, there is or isn't.
I'm checking it, okay.
No, well, no. I wouldn't care. I did it earlier this week, and I've. Let me just. It's the sort of thing you just don't look at because you copy it from a standard and think, oh, that must be right. Yeah, there's a gamma dashed in there. It's sorry, that is taken directly from DNV, current version of DNV, but there's a gamma dashed in there. Okay? And it's in the previous notes, but not these ones. So sorry about that. Mobilization displacement. When your pipeline starts to move upwards, there's not a lot of resistance immediately. It needs to go a little bit further to actually build that resistance up. And the DNV are very kindly, and this is right, they did correct some of this from the previous version, produced these charts. So if you've got loose sand, you've got alpha and beta. So if your full mobilization displacement is your ultimate resistance from the previous equation with the gamma dashed, and the 0.8 times the that in that range there is where sort of 75 to 80% of your total ultimate resistance will occur, will be achieved within 0.2 times the maximum displacement to a sort of plastic failure of the soil around the pipeline, the ultimate resistance that you get. And that will be 1.0, in the case of loose sand, 0.5 to 0.8% times the depth of backfill over the crown of the pipeline. And then there's similar values for medium dense sand and actually rock dump there as well. I've got a separate one on rock dump. Okay, now in clays, we have two potential failure mechanisms. This is like the one we described in sands, where that whole wedge of soil above the pipeline actually is pushed upwards. Because we're talking about an undrained shear failure, it's simply the length of that shear plane there that provides the shear resistance. We've got the weight of the soil plus the undrained shear strength of that material. The other thing which can occur, particularly in soft clays, doesn't happen in stiff clays usually because they're blocky materials, and in sands it tends to occur, but at two depths beyond where we'd normally backfill the pipeline. But in soft clays you can get a flow failure, because if you think of a soft clay as a sort of viscous material, it can actually flow around the pipeline. And you get what is described as a local failure mode, where the soil will be displaced around the pipeline as it moves upwards and just rotates, if you like. And we end up with those two models from DNV. NC is normally, for deep sea, it's our local failure here. NC, the theoretical bearing capacity coefficient, will be 9, give or take. It can be up to 12, but you nearly always use 9. Now, because it's a backfill material, it's going to be disturbed and remolded, and we allow for that with this value, an eta value, which is an empirical number based on field tests. Undrained shear strength at the centre of the pipeline, because it's actually remolding around the pipe, and then the diameter of the pipeline. So basically, that just gives you that limiting value for undrained shear strength, for uplift resistance in soft clays. This one, if you look, these two terms are exactly the same as the sand equation. It's just the weight of the soil over the pipeline. This one is 2 times the undrained shear strength. You've got 2 failure planes either side of the pipeline, and then you've got that depth, H plus D upon 2, and that gives you the undrained shear strength. Because there is no horizontal stress applicable, we're not modelling any horizontal stress in the clay, it's just a pure shear failure, so the actual force pushing it together doesn't make any real difference. It's undrained shear strength, so it's 2 times the undrained shear strength. Expressed as an average from the centre of the pipeline to the top of the trench. So if it gets softer as you go up, you've got to allow for that in your calculation. And DNV have given us some parameters in similar form to the previous ones. NC is 9. There is a sort of reduction if you're at shallow depth based on that equation, but in reality the shallow failure starts taking over, and you've got your 2 parameters there for mobilization displacement. Then I would stick to the equations I showed you. This is in DNV, but I would tend to use the equation I showed you rather than those two, although you end up with a very similar value. With H consol is trying to say that this clay is consolidated, so how do you allow for that? And then in a ploughed trench, sorry, sorry, you have those values which are generally similar. I'll talk about trenching techniques in a minute or two. Just to explain use of rock dump, that's a fall pipe vessel, so basically a ship, and they will typically carry about 20,000 tonnes of rock. So if you think of it in lorry, to put it into context, that's about 1,000 lorry loads of rock. So it's a lot of rock. And it just gets dumped on the seabed. And North Sea is quite cheap or relatively cheap to do rock dumping, because you go to Norway and there's fjords with rock at the side, and you dig it out of the side of the fjord, put it into a ship, and away you go. It's much more expensive to do it in some other parts of the world, like West Africa. And I do actually know of a ship that was sailed from Norway, a rock dumper, that we had to take a free span off, and they sailed a shipload of rock to Australia and used it to help smooth the pipeline profile. But what you basically have is this tube, and then you have a ROV on the base of the fall pipe, which can sort of move itself around, and as you're dumping the rock, you're monitoring the amount of rock you're placing and where it's going, and you can see that in real time in the control cabin, and they just dump the rock on the pipeline. It is actually amazing how accurate they are. I've seen, sort of pads laid for working platforms, and they get it to within about 5 centimetres or so. Amazing. And some example parameters there for rock dumping. Next slide is that one. And they're what I would tend to use in most materials. One thing which I haven't mentioned is that blocky clay, if you have a stiff clay, it doesn't mould plastically, it tends to be broken out in lumps. So when you push it back into the trench, it remains as lumps. And then, because it's in lumpy material, it doesn't have an undrained shear strength, it'll tend to act as a coarse, granular sand, gravel type material, so it will be blocks. And you use an uplift factor and this sand equation, okay? Centrifuge testing, I mentioned before. The big advantage of that is we take a sample of seabed soils from the project we're working on, remould them in some way, and with a relatively small sample we can replicate effectively the trenching process and pull the pipeline out. And the reason we do it in a centrifuge is the high G forces mean that if we want to model a sample at, say, 1 metre depth, a pipeline at 1 metre depth, you would normally need a metre of soil over that pipeline, which is quite difficult to get the same stress at the pipeline. By spinning it in a centrifuge, if it's at 10 G, then you get the same stresses at 10 centimetres depth as you would get at 1 metre. So you end up with 1/10 of the sample. The next thing is, if you've got a soft clay and you want to model the time that clay consolidates under self-weight from the trenching process, that's a function of both the in situ stresses, which are sort of squeezing the water out, if you like, and the drainage path length, how far that water has to go before it's out above the soil, if you like. Now, with that, if we run a centrifuge at 20G, it's like 20 times 20 in terms of time. So 20 hours at 20G is equivalent to 1 month, 400 hours. Is that right? Yeah. So we model a shorter time period much more quickly, and therefore model the consolidation of the clay. So it's very useful, particularly if we're doing some jetting or backfilling in soft clay soils, that we can model it at a small scale and in a quick time period. And the centrifuge is basically this type of device, a big drum usually there, which swings out over that's the centre point there, so that all swings round, and as it speeds up, that swings out around that pivot, and we set the model pipeline there in a sand bed in this case, and then the bar there you can see actually just pulls the pipeline up, and when we're spinning, when we can actually watch the pipeline and measure the load and the displacement of the pipeline. And that's the sort of result we get. So we're replicating very clearly the test, the initial pull out of the pipe, the maximum resistance it experiences, and then as you keep on pulling it, you can see it's only gone 60 millimeters there, and it's pulled effectively out of the seabed. You do have to be a little bit careful, and that's just highlighted. That's the sort of thing you can get if you haven't set it up quite correctly, but it does work, and you can see the result is similar. It's a good method of just proving the uplift values you're using in equations. Now the other thing, we've talked about backfill and the upheaval buckling resistance of the backfill. But what we'll also want to do, or what the pipeline designer will want, is the thermal conductivity of the soil. So if it's a high thermal conductivity, the pipeline's going to cool more quickly. If it's a low thermal conductivity or high thermal resistivity, it's going to keep the pipeline much warmer. So it's an input into the pipeline engineering process. You need to measure it, and the way we measure it is usually with what's American Society of Testing and Materials needle probe. The thermal conductivity is actually mostly dependent on the moisture content, and water is actually a better insulator of temperature than soil. That's provided the water isn't free to move, it doesn't just flow. So some typical values there: very soft clay, low thermal conductivity, whereas a sand, very soft clay will tend to have a high water content, so it's a low thermal conductivity. Sands and stiff clays will be higher because their water content is lower, and often people use a 2 watts per meter K as a sort of first pass for design. Well, if you know your job and know the geology along your route from a pipeline route survey or desk study even, you might have a pretty good idea that it's actually lower than that. And there are some charts published which we can use to estimate the thermal conductivity of the soil. So you can see here with both of these charts, and they're actually quite similar. Quartz content, if it's 100% quartz content, that quartz implies it's sand. So that would have zero clay content, would probably be close to 100% sand content. And they're reasonably similar. They're not exactly the same, but they're reasonably the same. So we can estimate it from water content and what the sand clay content is. And you can see how much lower it is if the water content is high. What I'll do now is spend a few minutes talking about plough or trenching. 3 main methods for trenching: ploughs, water jetting cutters or trenchers, and then cutting machines, trenching machines often. Each has their own strengths and weaknesses, and there's several cases where one will be more suitable than the other. So we need to select the right trenching tool. One of the analogies I would use here is if you have want to dig a trench on shore, you ring up and get a JCB, and you find it's actually a bit stiff for the JCB. Well, that's okay. You can get somebody with a tracked excavator without too much bother, and it's only a couple of guys. And you know, okay, the tracked excavator will have to come on a low loader, but it's not difficult to get hold of. If you're trying to trench offshore, then your vessel will probably have about 80 people on it. It might take you a day or two to sail the site alone, and it might you can't just ring up, and there's just not the number of assets around to be able to ring up and say, oh, we'll have a different asset. You might need a completely different ship to do the work. So it's important that you understand the burial requirements, the seabed conditions, water depths, because some trenches are very difficult to use in some particular water depths. Clay ploughs are very difficult to use in deep water and very shallow water as well. Things like route length. Plough is much more efficient for a long route because they tend to be relatively fast. Certainly in stiff clays are particularly good, but a disadvantage of a plough is if you've got a lot of crossings and you're working close to infrastructure, you're going to have to recover it, and they're big things to recover, whereas a jetting tool is much easier to recover. So soil type, that gives an indication of the types of soils where what are most appropriate for different techniques. Jetting tools, the blue there, very soft clays, they're very suitable, and most sands, all really, possibly even into the very dense sands there, you could still use a jet tool quite successfully. But ploughs, you can use them very soft clay. Where they do really score is in this range, particularly in the clays. They're very efficient in stiff clays, far more so than a jetting tool. And a cutting machine, a mechanical cutting machine, they will get into things which ploughs can't get into, but they'll be very slow and expensive to use, high downtime because of maintenance and such like. I know this has got cable ploughs in it, so we're just going to concentrate on pipeline ploughs and backfill ploughs. You need a plough to cut the trench and another plough to backfill it. Water jet trenching, quite a number of assets out there, from quite small ROVs to 2 megawatt pipeline jetters, and 2 megawatts is a lot of power. And mechanical cutting is there. Really for pipelines, it's chain cutting techniques, hard clays and soft rocks is where they're most effective. Yeah.
What depths are we looking at?
For trenching.
Yeah.
From the shore end, if you go to West Africa, say, you probably trench most pipelines down to about 100 metres water depth. North Sea, you'll trench up, well, pretty well old pipelines, all smaller diameter pipelines. In up to say 400 metres water depth in the Norwegian Trench. In America they trench all pipelines to about 60 metres water depth, and then they don't really bother so much after that. However, if the requirement is for thermal insulation of the pipeline, then I've seen jobs trenched down to about 1,000 metres water depth. Okay, so it's, you know, there's no real single answer. The advantage with deeper water pipelines is they tend to be soft clay jobs and a jetting tool, and that's much easier to use in deep water. Okay. I had a client, a good client of mine, they wanted to build a mechanical trencher, and they were adamant it was going to be able to trench at 1,000 metres water depth, and I said all along, you'll never use it at that water depth, you'll never use it at that water depth, and they haven't. 10 years later, but you know, it's never, I don't think it's ever been over about 200 metres water depth. And the cost impact is significant because you've got to design an umbilical, you know, to carry all that power. And then you end up with a bigger umbilical, you need a bigger umbilical winch, and it just goes on, and it's crackers. Just talking about pipeline ploughs, technically it's the best burial method, I would say. It usually is. But in terms of trench profile, you get a very good trench profile, and a well-defined trench, and they can trench pretty well all materials. A big problem is this thing, high bollard pull. You need 250 tons realistically, and ideally a bit more than that. And there's not many ships like that, and they burn a lot of fuel, so they're difficult to get. What we do is create a V-shaped trench, which I'll show. Sorry, just a second. V-shaped trench. So the plough picks up the pipeline, and then as the plough passes, it sits down into the trench. I'll talk about multipassing a little bit, but what you can't do is go close to existing infrastructure. You're pulling it with a ship, and if for any reason the ship runs on, or if you hit an area of softer soil, the plough can launch forwards, and then you can hit somebody else's pipeline, which you don't want to do. Leave those. That's a fairly typical plough, CTC, now deep ocean plough. And that's about, you can see how big it is from the truck in the background, and it weighs 120 to 150 tons typically. So they're big, heavy things to use. You need a big A-frame, big ship to pull it, etc. So not cheap to mobilise. And this is the way we do form the trench. In the first pass, might be like that, with the material cut out there and placed at the side of the trench there. Now in some cases, in a lot of cases, that might be sufficient, and we end up with a trench like that. But we may want to go deeper, in which case we move the spoil out over and then do a second pass with a plough and relieve a trench like that with the spoil heaps either side. And as we go along, the pipeline's in the base of the trench there, that's fine, but we want backfill on it, so we have to use a backfill plough. And you can see the big thing here, which simply bulldozes the soil back into the trench and provides backfill over the pipeline like that. just to talk a little bit about the forces on the plough and why it is beneficial to how a plough deals with different soil types. You have a soil reaction on the share, now, which is sort of pulling it into the seabed, but the plough at the back is being supported there by the heel of the plough. Now the good thing about that is if you're in soft soil, the plough will do what we call pitch aft, sort of sit down, and it will create a slightly deeper trench, but it's being supported there. However, if we're in hard soils, then it's all the weight, the plough pitches forwards and all the weight goes on there, so it's always trying to get back to that equilibrium position of basically having a horizontal keel. And because that change, whenever it happens, doesn't happen immediately, it means that you get a very good trench profile, and the straighter, the flatter the trench profile is, the better that is from an upheaval buckling point of view. Okay. The plough performance is affected significantly by the seabed soils. If we take the various components, in sands and clays, we've got a frictional value effectively, which is actually reasonably well defined in most cases, or pretty well all cases. We then have a static component. In sands, that's actually relatively small. In clays, it's a simple passive resistance calculation and fairly well defined. In clays, the dynamic component we can estimate from testing clays at different shearing rates, and is actually fairly well defined, so that's not too much of a problem. The big problem we have with ploughs and sand is estimating this proportion, the dilation and permeability of the sand, and the reason for that is if we look at the speed effect in sand, when you've got the sand particles tightly packed together, when they shear, they're trying to move apart. That gap is opening up in front of them, in the sand mass, in front of the plough share. Now, for that to happen, water's got to flow into those void spaces. And sand is a reasonably permeable material, but it's not highly permeable. The water doesn't flow immediately in, so you end up with a sort of force balance whereby as the plough shears the sand, it moves apart, but then water's trying to run in, and as that water is trying to run in, it's actually creating a pressure difference which is pushing the sand particles together. So an analogy is, if you walk down the beach on dry sand, air can flow very easily through that sand when it's dry, so it moves around. But once you get onto wet sand, it feels quite hard. And you see that with a plough. So ploughing in sand is a difficult thing to predict. And you end up with these two curves. If it's fine, i.e. low permeability, to get any speed takes a lot of toe force. If it's more permeable, then it becomes much easier to trench. There is a slight limitation that in shallow water, realistically, it only would happen in shallow water. It could actually cavitate. You just get a vacuum, and that's the limit to your sort of pressure differential. Loose sands, where the sand particles are already sort of like that, they already have a high void ratio, are pretty easy to trench, but you very rarely come across it. And clays, soft clay and stiff clay are, fairly easy to predict, and with a reasonable degree of confidence. And certainly soft clay, you can do 750 metres an hour in soft clay, and you're really not going as fast as you could do, because you've got to pick the pipeline up and run it through the plough, and you don't want to damage the pipeline, so you want to maintain some control. And that's an example of a backfill plough, just so you can see it. You can see how it's folded up there, the main shares which are open out to push the soil back into the trench, and the front skids there are sat like that, so they sit in the V of the trench. One point to make is this one, minimum SG requirement, and the reason for that is as you push particularly a sandy, silty type soil back into the trench, it ends up as a dense fluid, if you like, and if your pipeline isn't heavy enough, it floats in that fluid. And so you push the material back, your pipeline floats up, and you're stuffed. Basically, you've done all that work for nothing. And I've seen that happen on several occasions as well. And to be fair, not for 15 years or so, because everybody's fully aware of it, but I have seen it happen where people have gone out, trenched a pipeline, backfilled it, and done a survey and said, oh, it's on the seabed. Oh, what are we going to do? So,
would you try and coordinate that so you backfill when you were hydrotesting or something like that?
well, you usually, the ideal thing with a pipeline plough is to trench it empty, because it's easier to pick up, it lowers the stresses on the pipeline, and backfill it when it's flooded. But it's not too difficult to do that, because you've got one plough on the vessel for trenching, and then you go back to port, pick up another plough to do the backfilling, so you can sort of manage that process reasonably well. That just illustrates the importance of getting the how the backfill goes in, and how important specific gravity of the pipeline is. Jet tool trenching is a good method of trenching in sands and soft clays. It really is very effective. One of the things in sand is you trench, you fluidise the seabed, pipeline sinks down, and you'd usually have try and have the pipeline flooded for a jet trenching operation, and then the backfill settles naturally out of suspension. So in sands, jetting is good. Soft clays, it's good because the soft clay is fairly easy to jet, but you don't get any backfill unless you do a trench collapse pass. And from a cost point of view, you don't need a particularly big vessel, just a fairly cost efficient, relatively small DP2 vessel. Of the disadvantages, the most important one is selecting the big enough trencher for the material you've got. Using an underpowered trencher is just hiding to nothing. And there are some configuration methods that you can choose. You can have it on a track base, drive along the pipeline, and I would argue that's usually the best one, because you've got good control of your speed and currents aren't trying to push you off sideways. So most of the the operators I know prefer to work on track bases. Another advantage of the next one is free swimming, where you've got some skids on the bottom of the trencher, but basically something just to stop it sinking into the seabed, give you a sort of benchmark for swimming along the pipeline. The advantage is, on soft soils you don't have a problem with sinkage and slippage and so on, but the disadvantage is you do actually lose a lot of power in terms of jetting power, because you've got to propel yourself with thrusters along the pipeline, and then sometimes you also have to react against the water jets that are trying to push you up over or down over, depending on which way the nozzles are orientated. You've got to resist the pressure from the nozzles. And pipe riding is there, where you actually have some rollers which clamp onto the pipeline, and you can swim along the pipeline or drive along the pipeline. They're not that great because they're only really effective or if the pipeline's partially embedded, the rollers start contacting the seabed and then getting stuck. And if you've got a piggyback, then do you know what a piggyback is? I can take it you do. Another pipeline on top of a larger pipeline. If that goes round somewhere else, then you can't use the pipe riding rollers. So I know of people who have pipe riding rollers, but nobody really uses them. The way we jet is to have two sets of nozzles, one for actually cutting and forming the trench, and then which are the HP nozzles, and then the LP nozzles, low pressure, keep the material in suspension as the trencher goes forwards, or we might use them to actually remove soil from the trench. So if we look at the way we do it, if these forward high pressure nozzles are actually creating the trench, breaking up the clay as the trencher goes along, the pipeline's sitting on the seabed, and as the trencher progresses, it's sinking down to the back of the behind the trencher. And then we have the low pressure nozzles keeping this material in suspension, and then as the trencher progresses forwards, that there settles out of suspension. That comment there, 26 millimetres, is relates to a specific trencher. It depends on the trencher what size they are. It is best to have a high pressure, low pressure system. It's much more efficient in terms of power. And I've said most of that. The only other thing I would make is speed of the trencher is key to getting good results. If you want to go, the trencher wants to be progressing as smoothly as possible. Not speeding up, slowing down, because that would cause the sand to consolidate at different rates or different distances behind the trencher, and then you get out straightness incidents. Clays, we're normally cutting a clay rather than actually fluidizing it, and that tends to leave some lumps of clay. But with the right nozzle selection, we'll break it up into manageable sizes, and then the backwash moves the soil back down the trench. It's much harder to set a trencher up for clay than it is for sand. And if you look at this is the sort of thing we look at when we're designing a trencher for sand or engineering for a particular job. You've got the main jet legs there. There's always two jet legs in the pipeline. It'll be up there. And they're clearing a path for the jet legs to go through. But we also need to clear material out from between the jet legs, so you have some nozzles facing inwards. In some very soft clays, the trench side won't be stable, and we can actually cut at the slope on the side of the trench by having some nozzles jetting outwards as well. So that's an example of a jet leg there. So you can see the forward nozzles down there, and then there the side nozzles jetting outwards. And that is an example of the sort of trench you can create. Nice, clean trench you can see, and that's the pipeline in the base of the trench. And the fish swimming off to the side there. Sure. Yeah. They're not too fussed about little trenches riding along. There's some example trench profiles. You can see in soft clay what if you're having to ducted material out, that's the sort of profile you get where you've got a nice vertically sided trench with a little bit of backfill, a little bit of slurry over the pipeline, but not a lot. In firm clay, we can't break it up as much, and you can see, you know, that sort of shape. You haven't cleared the clay out from between the jet legs properly, and there's lumps of clay being pushed up just to the side of the trench, and the cable or the pipeline hasn't gone that far down in the trench.
What's the depth of these jet legs?
Well, anything up to 3 meters is fairly common. 2 meters is the most common.
So
But
it means that 3 meters is the depth of your
trench, yeah. That would only be on some of the bigger trenches, though. Most have 1.6 to 2 meter jet legs, and some you can use smaller ones as well. You know, if you've got a hard clay, you don't need it, or a firm clay, you don't need to trench it as deeply, and also you want more power per unit area of trench, so you make it shorter. A loose sand, you can see both sand cases just get free backfill basically, just material just settling out of suspension. The interesting thing is you get a slight dish in loose sand, but it's much more defined in dense sand, which is just an interesting thing. In soft clay, what we can do is educt material out of the trench to leave it open, as that photograph showed. But if you want good quality backfill, the best way to achieve that is actually to collapse the trench sides onto the pipeline. So we do that by having a device like this, which both jets up from the base of the trench and out there, and it basically defines that block of clay, which then slides in towards over the pipeline. And that's a good and effective method of getting backfill in soft clay. Just moving on to finally to mechanical cutters. There are 2 examples there. One's on the back of a ship. Both of them are fairly similar in that they've got tracks, you can see, and then those things there actually pick the pipeline up, and it's supported on rollers. There's a roller there, you can see, in the roller there, and there the grabs on that one. And there's a chain in the middle, and it cuts a vertically sided trench in the seabed soils, and the pipeline goes down into it. The disadvantage with those is that you get little or no backfill. You've got to do something else for backfill, really, because the soil is often dispersed. So it's not great for backfill, and they tend not to be great for outer straightness as well in the trench profile. It responds poorly to sort of, you get a boulder in the trench, which is quite common in stiff clays, and you get an outer straightness incident. So they have their place, but they're not that reliable, not that great to use. Okay, there's some references for you, the ones I gave at the start, and also DNV. The DNV F110 you can download from the internet as well for free, but you've got to go to the DNV website, don't go to British Standards website. Okay, I think we'll leave it there. I was going to start the other lecture, but I think I've probably gone on a little bit.
next day.
Yeah, well, tomorrow, I think we've got to be out by 4 today, so you've got me tomorrow, I'm afraid, sorry. I'll correct that error in the notes as well tonight, and I'll get it to Yongshan for your consumption, okay? Same place and time tomorrow.
What's happened to you? Whenever they were tired, they would stand up.
But you said that you were going to design
Question regarding the jetting tool.
Sorry, yeah,
The
yeah,
water
yeah.
jetting. So I think initially there is no trench section. So the when they use the jetting tool the first time, I think the seabed is flat. So how can we make the initial process? Initial depth
right.
to-
What the legs can go up or rotate in the trencher. So they, as you start trenching, you lower them down progressively.
Like this.
Yeah. So you sort of you transition in basically. So you're driving along, and your leg, if you like your legs there, that's just one of your tracks, and you're going along. And as you drive along, your leg just goes down. They're all, they're quite complex machines.
So okay. So the length between the legs depends on the pipeline.
It depends on the pipeline. Most of them you can open and close them like that, so you try and keep them as close to the pipeline as you can. And then when you come to an anode, you open it out and then close it again. Or when you're starting off, you might have them fairly wide as well.
The use of the default jetting tool is after we lay the pipeline.
You are always jet a pipeline which is there. You don't. I've never heard of anybody trying to make a trench with a jetting tool for subsequently placing the pipeline in. With pipeline ploughs to create a V-shaped trench, and some people will try and lay a pipeline into that trench, but it's quite rare. It's actually easier to follow the pipeline, and the other thing is if you pre-cut the trench and lay the pipeline into it, you've got a really narrow lay tolerance, and if you don't do it quickly, you can get some natural backfill into the trench. So then you formed the trench and you've lost that much of the depth because of natural backfill. You see?
So that means that the plow is the rarely used because
the plow. It depends on the type of job it is. If you've got a long pipeline through stiff clays there and not many crossings, then the plough's ideal. If you've got sands, then often the jetting tool is the most efficient method to do it, because with jetting in sands you can do 300 meters an hour, say 200-300 meters an hour. Ploughs you can be down to 50 meters an hour. And the other thing with a plough is you create a V-shaped trench, and then you've got to go back, or usually go back and put the backfill back in. Whereas in sand, your jet tool, you trench fairly quickly, and you get natural backfill, so you don't have to go back. And you've got a lower cost vessel, so in the sands, jetting tools are generally much better. Okay, but they don't work very well in stiff clays. You might not get much of a trench, and then you haven't really achieved what you wanted to do, and all the rest of it. So. Okay.
Yeah. Okay. Thank you very much.
Right, no problem.